I'm Provost and Executive Vice Chancellor Ralph Hexter. It's my pleasure to welcome you to the second event in the 2018-19 season of the UC Davis Forums on the Public University and the Social Good. The UC Davis Forums was established in 2012 and presents about a half dozen lectures each academic year by experts from a range of disciplines. The series was designed to promote informed and thoughtful dialogue among members of the campus and the public on the following subjects: the major challenges facing the public university, ways of responding to those challenges, and how the public university is evolving, with an ultimate goal of helping to produce a public university that will best serve society and individuals. This series poses some questions. Particularly, what should and can the public university be in the 21st century? In our preceding 6 seasons, the UC Davis Forums has presented distinguished speakers on a wide range of topics pertaining to the public university and the social good, including educational access and affordability, diminishing public confidence in and funding for public institutions, and equity and diversity in the academy, among many others. I invite you to visit the series website, forums.ucdavis.edu, to find information about all of this season's events as well as videos of our past events. In several earlier forums, we explored different aspects of the public university's research enterprise, including its contributions to regional prosperity, its responsibilities with respect to urgent societal problems, and challenges associated with funding and metrics of productivity. Today, we extend that focus to address an aspect that is central to the value of all universities: the quality and reliability of our research. In this connection, we're delighted to welcome John Ioannidis, holder of the C.F. Rehnborg Chair in Disease Prevention at the Stanford University School of Medicine. Professor Ioannidis will speak on the topic, Reproducible and Useful Research, Building Trust in Our Science. This topic alone will, I think, appeal to everyone who cares about research and public attitudes towards science. What makes this forum a can't-miss event is that there's no one more qualified to speak about this issue than Professor Ioannidis. Indeed, his 2005 paper, Why Most Public Research Findings Are False, has been the most accessed article in the history of the Public Library of Science, garnering more than 2.5 million hits. Professor Ioannidis will get a proper introduction shortly, but before that, I have a few thank yous and announcements. I'd like to thank all who made this event possible. First and foremost, Professor Ioannidis for traveling from one former farm, Stanford, to this former farm. We're eager to hear what he has to say. Next, the UC Davis Forum Steering Committee, led by Martin Kenny, Professor of Human and Community Development, and also our moderator for this event, Samin Vazir, Professor of Psychology. I also want to acknowledge the campus units that have joined my office to sponsor this lecture: the Community and Regional Development Program, the Center for Regional Change, the Ethics Commons, and the Bioethics Program at UC Davis Health. One more announcement. After today's presentation, there'll be a question and answer period moderated by Professor Ioannidis, and then a reception right outside. We hope that you can all stay for talk and refreshments. And now, Professor Vazir.
Thanks. I'm delighted to be here introducing John Ioannidis. Some people would say that John Ioannidis has done more than anyone else to undermine public trust in science, but exactly the opposite is true. Bad science is the perfect climate for science denialism and quackery to flourish, and John has been on a relentless mission to try to make science better, which is, to my mind, the greatest gift you can give to science. So I think the scientific community and everyone who relies on science, which is basically everyone, owes John a great debt of gratitude. The best example we have for why the public should trust science is that John is one of us, and many of us recognize the immense value of his contributions. There are many ways to measure John's influence. Using the traditional metrics, he's been wildly successful. He's the most highly cited researcher on the topic of research methods, according to Google Scholar. He's flooded with invitations to speak to prestigious groups, and many people, including the most powerful and famous people in science, want to associate themselves with him. But I think John would agree that these aren't the only metrics that matter. And John, to his credit, has not been satisfied with all of this attention and praise. John has even lamented that many people who praise his work don't acknowledge that the problems he points out apply to their own work. Indeed, you can see in his publication record that he frequently chooses to work with early career, relatively powerless researchers rather than the big names who invite him to collaborate. And from talking to many of these early career researchers, I can tell you that he's universally respected and admired by his collaborators and mentees, which is perhaps the most impressive line anyone can have on their CV. John also isn't without enemies. In one of his papers, he describes a conversation with a colleague in which his colleague jokingly told him that he should be careful lest hitmen show up at his office. John, in his characteristic humility, replied that the hitmen should make sure to turn left when they come up the stairs because he would feel terrible if the hitmen strangled the wrong person. This is a funny anecdote, but it illustrates a fact about John that is probably underappreciated. He must have a tremendous amount of courage to do what he did when he did it. Speaking out about reproducibility problems isn't easy even now, but I can't imagine the resilience it must have taken to do so when he did, in the climate he did it in. Most of us would surely have given up in the face of the resistance he encountered, but we're very lucky that John did not give up. Even today, in the face of mounting evidence that John was right about the gravity of the situation, there are many who argue that he should stop, that we should not be airing our dirty laundry in public because it gives fodder to those science denialists and quacks. But as John has pointed out, this is exactly backwards. In his own words, quote, "If we don't tell the public about these problems, then we're no better than non-scientists who falsely claim that they can heal. The scientific enterprise is probably the most fantastic achievement in human history, but that doesn't mean we have a right to overstate what we're accomplishing." I think it's not an overstatement to say that John's work has affected all of us, whether we realize it or not. But as a psychologist, I think I've benefited even more from John's dedication to improving science. In 2011, long after John had been warning us about these issues for years, my field of social and personality psychology was forced to confront this problem. Since then, we've been recapitulating many of the same debates and arguments that John has been fighting in medicine. And thanks to his careful and painstaking work, we've been able to fast-track many of the reforms that will hopefully make our science better. But as John has also pointed out, we need to be careful that these new practices don't get co-opted as just another vehicle for prestige. My own research is in the area of personality psychology, and specifically, I study whether people have self-knowledge of their own personality. So I was very excited when I read in an interview when John was asked to describe his own personality in 3 words. John described himself as an uncompromising, gentle maniac. As an expert on personality and self-knowledge, I'm here to tell you, John, that that is in fact the correct answer. It is my extreme honor to welcome this uncompromising, gentle maniac, John Ioannidis.
Thank you for this wonderful invitation and for this great introduction. I'm here to share some thoughts and hopefully have time to discuss and learn from you because I'm still in my early learning phase when it comes to reproducibility and usefulness in research. I will start by showing you one of my best studies. Why do I think that it is one of the best? I work with fantastic colleagues, extremely qualified, very knowledgeable. We worked for 3 years. We had a lot of data. We cleaned them very carefully. We had superb methodologists and data analysts in the team. We did analysis according to our protocol. It was the largest study done in the field, 10-fold larger than others. Really conclusive title, UCHL1 is a Parkinson's disease susceptibility gene, published in the best journal for neurology, Annals of Neurology. 2004, moving 2 years forward. Here's another study in that very same journal by extremely competent scientists, extremely well-trained, some of the best methodologists again in their team, combining expertise and with a sample size about triple our sample size. And then you combine these studies and there's another paper that says, yes, there is a signal there. We were right. But then others say we're wrong. The other team is right. And before moving in the room, I just checked the latest update in the NIH Genome Resource Facility, and it says it's not clear. So this is not pretty uncommon, and this is actually a situation where we had extremely good circumstances compared to the circumstances that we have in most other types of work that we do, where we have limited funding, very small studies. We can take a shot at suboptimal analysis just because the data are not any better to tolerate. This is the universe of science. Actually, just a recent snapshot of that. This is just 20 million papers out of about 180 million that have been out there and increasing at a rate of about 6 million per year currently. There's 13 major sectors in that universe in different color, like medicine is one of them. Chemistry or physics are others. And I have pointed an arrow there to something which is my best paper, a speck of dust in a speck of dust in a speck of dust, somewhere around there. So it's very difficult to make any claims about knowing what we know unless we can take a look at the big picture, unless we can zoom out, take a look at that universe, see how it behaves, see how it's functioning, how it's working, how it's multiplying, and where is it heading. So there are some patterns on where it's heading. One pattern is that everything looks great on the surface. A few years ago, we looked at everything that had been available in PubMed, so the entire biomedical literature since 1990, 15 million abstracts and about 1 million full-text papers, about 800,000 to be exact. And whenever there were p-values, either in the abstract or in the full text, 96% of the time, the results, there were statistically significant results. Everything seemed to be significant, everything seemed to be novel, everything seemed to be very nice. I would argue scientific discovery has become a very boring nuisance if that's the case, because there's millions of papers published every year that claim innovative, novel, significant results. And it would be fabulous if all of them could materialize. We don't know how many of them are genuinely true and not false positives, and we don't know how many of them will materialize. I can tell you that for the UCHL1 debate, until now, which is almost 2 decades later, this has not become something useful that I can tell people that they can get some utility of that information. Translation takes a long time. This is from an analysis that we had published in Science 2008. We took the creme de la creme of medical papers, the most highly cited ones, more than 1,000 citations in Web of Science at that time. And we went back to see when this story had started. Apparently, these papers were proposing that we have some very nice, effective treatments that can save the world, save lives. So we went back and we realized that it takes on average about 25 years. In some cases, it takes more than 200 years to see that translation. So nitric oxide was described in late 18th century. Then Sir Richard Daly tried to experiment with it on himself. He almost killed himself, and then people didn't want to try it again for a pretty long time. There are a few exceptions. There's HIV triple therapy that moved very fast from the design of protease inhibitors to developing effective treatments that would be tested in randomized trials. I was at NIH at that time. I participated in the clinical trial that showed that HIV can have its mortality dramatically curtailed very fast, within 3 years from the basic science discovery to translation. But on average, 25 years, sometimes much more, and 40% of these papers actually were overturned within a few years. So the black points on the top are even larger, even better controlled studies that tested the very same effects and found that they're not there, or they're very small and they're not as likely to be so beneficial. How do we sort out what would really translate, what would really be not just true, but also useful? There's a wave, there's a revolution over the last several years that maybe the answer is in reproducible research. That if we have research that we can trust, good quality research, research that we can repeat and get the same results, this will be pretty much the secret to get things to work the way that we want them to work. Across all 21 major fields of science, that slide shows that there is a geometric increase in the rate of the use of that terminology, reproducibility of results, or reproducibility of X. But what does reproducibility mean? If you ask 50 people, you may get 50 different answers. And basically, these answers can be grouped into 3 major bins: reproducibility of methods, reproducibility of results, and reproducibility of inferences. Reproducibility of methods means that if I have some software, I have some script, and I have some database, some data, some raw data, if I put them together, I get the same result. That sounds very nice, and it should be very straightforward. The problem is that very rarely do we have the data. Until recently, that was a very rare exception. Publications were more like advertisements. I have published this, which means I have done this research. Trust me, I'm publishing this advertisement. Trust me, it is there, but the data were nowhere to be found. Sometimes the software is not available, and very often the script is not available. So even though it is desirable, we cannot really probe into that. Reproducibility of results means that I do another study and I get the same results. And then the question is, who is going to fund that study? Who is going to pay for that replication effort? Reproducibility of inferences means that I have one or multiple studies and I ask people, what do you make out of those? And I'm going to make some recommendations, and people may not make the same recommendations out of the very same data. How many of you are working with small studies? You would love to work with bigger studies. Okay. How many of you are working with big studies? Okay. So if I were to ask that question maybe 10 years ago, there would be very few people who would say, I work with very big studies. But now I think that we start seeing both a continuation of the small study paradigm, but also the new big data paradigm. There are some typical recipes on how things work with small data and with big data. With small data, the typical problem is that you have limited resources. The pie of funding and resources is certainly not as big as we would wish, and I have always argued that we need more funding for science, but until policy people and politicians hear about that, it may take a while. And therefore, each one of us can run pretty small studies. We work alone, mostly, and we have to prove that we can work alone, that we are principal investigators. We can be isolated and still function. We can be competitive. We need to show that we are competitive. We need to get nice-looking results. This means that we need to make all use of the data. There's a lot of post-hoc exploration. There's a lot of leniency in making claims in terms of statistical terms. A p-value of 0.0499, either in the original analysis or in the 20th attempt to reanalyze the data, is pretty good enough. No registration. There's no time for registration. Most of that research is exploratory. No data sharing, because it's thought to be offering ammunition to competitors who will be competing for the same pie of money. And no replication, because you spend 2 years to run a study, and then you have to spend even more time to do a replication that may show that that was not correct. And then you're back to square zero, that I have nothing to show. With big data, there are differences. The typical situation here is that I have more data than I wish. These data keep accumulating themselves while I'm sleeping. If I'm working with electronic health records, I go to sleep, and next morning there's several tens of thousands of patients worth of data across the country or across the world that have just added themselves to my database. I've never met these people, never shook hands with them, never really saw the data. Sometimes I have no clue what these data are about. They just come to my computer at some point. I still need to find success stories, so I still need to do a lot of cherry picking and find the best looking results. Much of that is done post hoc. In many of these cases, as I say, I don't even know what these databases look like until very late when they arrive in my laptop or in my cloud. Statistical inference tools are a bit more sophisticated on average compared to the small study world. So it's common to see some Bayesian statistics, some fault discovery rates. If you see frequencies modes, you may see some more restrictive requirements asking for lower p-values than just 0.05. But there's very little consensus across fields that might be using what is otherwise the same type of prototype of data. There's some consensus within families of subfields that do very much the same thing, but if you compare nodes across neighboring fields that should be using the same statistical techniques, maybe they don't, because they kind of grew independently. Again, very little registration for most of that research, and data sharing is more common in that world, but the problem is what is being shared. Sometimes neither the data generator nor the data recipient knows what it is. Code books might be erratic or elliptical or esoteric or cryptic, or all these are Greek words. You want to know more about the data that look like a black box much of the time, and you're learning as you're producing, which is interesting and may lead to some interesting observations, but sometimes you may have spent a year, 2 years, 3 years, and you recognize that, oh, I had made some very basic assumption that actually, now that I know the better a little better, is not really true. Another approach to assess reproducibility is brute force reassessment of classics on purpose, trying to reproduce the exact experiments, the exact studies, and see whether we get the same results. So psychology is clearly making a difference in that regard, and it led some of the recent efforts that have inspired also a number of other fields to test some of the creme de la creme, most prominent papers published in the very best journals in the field. And this is the classic paper that came out in Science 3.5 years ago. 273, if I believe, teams of psychologists joining forces to look at 100 papers published in their top journals, and this is how it looks like. There's different ways to read the results, but roughly 64%, 2/3, are not reproduced. Regardless of how you look at the reproducibility track record, p-values or effect sizes or confidence intervals or ability to get a significant result, it doesn't really look very good. And then there's several other such efforts. This is one that was published about 4 months ago, 6 months ago, and it looked at papers published in Nature and Science arguing that maybe these are the 2 top journals, and maybe you expect to see some better reproducibility there. Not really much different. Depending on how you look at the data, maybe it is a little better, but on average, if you read an effect size in Nature and Science, when you get the reproducibility effort, it's about half on average. And sometimes it's nothing. Sometimes it's just less. It's 75% on average compared to what the original was. This has led to lots of new insights, but also to what I call the reproducibility wars. Whenever a study is not replicated, quote unquote, or without quote unquote, not reproduced, quote unquote, or without quote unquote, there is tension about what's going on here. There's people who feel that reputations are at stake, that someone cannot be allowed to make an error. Personally, I feel that I'm in science because I want to be allowed to make errors. This is why I love science. If not, I would go to politics or religion or something else. But it's not easy to tell someone that, this big thing that you had proposed, I tried very carefully. Actually, in these reproducibility efforts, I even told you how am I going to do it. I even gave you explicitly every detail. You agreed. You signed off on that plan. And sorry, I don't get it. So reproducibility of inferences is becoming a major challenge because people now may say that the original was wrong, the reproducibility was wrong, even though it was so carefully vetted and signed off before it was done. Maybe both were wrong, or maybe both were correct, because there are some features that maybe we haven't recognized, that even though we tried to reproduce the original, we didn't think of these features that could make a difference and are actually making a difference. Can we take a look at large scale across science about reproducibility attempts? Well, before these very thorough efforts were done in psychology and then economics and then social sciences and other fields, people have been doing meta-analysis for a long time. You know, Pearson did his first meta-analysis in 1904. My mentor, the late Tom Chalmers, started publishing meta-analysis a little bit after the Second World War. And we have a lot of experience on combining and contrasting studies on the same topic, on the same question, done by different teams in different investigations. So along with Dan Fanelli and Rodrigo Costas, we looked at every single meta-analysis that we could get a hand on across all disciplines of science. Whenever we got too many, we just got 400 of them from the specific discipline. And we said, can we track some hints, some signs of bias operating in these blocks of evidence on the same question that would be compatible with the types of biases that are speculated to exist in the literature? For example, how often do we see patterns of small study effects, which means that the small studies give exaggerated results, or larger effect sizes, stronger associations compared to the larger studies? Now, what does that mean? One explanation might be that the smaller studies are more susceptible to selective reporting, selective analysis, publication bias. It's more difficult to make a mega study disappear completely. You know, it's like having an elephant in this room and you try to get it out of the room and it's stuck there. I mean, someone will hear, that study existed, what happened with this? Conversely, a small study done in your lab, I mean, who else is gonna know about it? You kill it and nobody notices. So we postulated that these biases, and we came up with a very long list of biases, would give a particular flavor to the result, a particular pattern to the results of meta-analysis. And we tried to see how often we see these patterns. The answer is we see them very often. Now, it doesn't mean that it's all bias. It could be, and it doesn't mean that if you don't see a pattern, there's no bias. For example, you may have a field where all the studies are flawed and they all get the very same, very nice result. And there's no heterogeneity, but they're all flawed. Until we find out 10 years later, oh, what were we measuring here? You know, we were just measuring noise. There were differences across major scientific disciplines in terms of the strength of these patterns. For example, for small study effects, which is the difference between small and large studies, there was a very strong pattern seen in the social sciences, a pretty strong pattern seen in the biomedical sciences, and not much seen in physics. And you know, physics, lots of physics has no small studies to start with. They just work with these mega data sets that they analyze, have 30,000 people looking at collections of petabytes of data. Gray literature, decline effects over time, early extreme results that kind of balance them out later on, citation biases, US or other country-based biases were also seen, but sometimes they were more strong in some settings than others. Let's talk about the second dimension now, beyond reproducibility. Let's talk about utility. Research may be reproducible, but it may still not be useful. And for research that is pretty early in the chain of translation, what we call blue sky, quote unquote basic science. I have a problem with the term basic science. I think all science is basic. But let's say research that is done without a specific deliverable. You just do something out of curiosity, you find it fascinating. You don't know what's gonna come up and you don't know how exactly you're going to apply it. This is wonderful research, blue sky science. You cannot really tell someone you didn't save the world, you didn't save lives. How could he or she know? But a lot of research is translational, it's late translational, it's specifically seeking to have deliverables. In medicine, where I work, much of that research that we do is promising some deliverables. I mean, we're not doing that just for fun. We see people dying around us in the hospital, a few blocks from the lab or from our laptops. So we need to do something about it. Unfortunately, most of that research that should have been useful eventually is not useful. And you may ask, how can you tell? Well, here are 8 things that I would like to see for research in medicine to be useful, and I think that that applies probably with some modifications in other scientific disciplines as well. I would like to see, first of all, a problem base. Is there a problem that we're trying to solve? If there's no problem, why are we doing this? Very often I see that there's no problem and we are creating a problem. We're making people feel sick even though they're not sick, and then we can treat them, but they're not sick. Context placement, what do we already know? And if we know enough, which we can tell with a nice systematic review, maybe we don't need another study. Information gain. Information gain is a term from physics. It's entropy change. Are we going to change the entropy of the system by adding this new study? And are we going to change the entropy regardless of the result? Because if we're going to change the entropy only if we get a statistically significant large effect size, then we're kind of chasing to get that particular result as a conclusion, and this is a bit biased. But how about if we get a quote-unquote negative result? Will that change the entropy of the system? And a nice done study would change the entropy of the system regardless of the result that it will get. You know, sometimes getting a positive result will change the entropy more. Sometimes getting a negative result will change the entropy more. I know of many nice negative studies that were tremendously important to do, and far more important than almost any positive quote-unquote study. Pragmatism, does it reflect real life? Are we thinking about something that is an artificial construct in the lab or affecting a few people, but then I will not be able to apply that more widely? Or is it pragmatic? This has become very popular, and recently we did an analysis looking at randomized trials that claimed to be pragmatic, and they even had that in their title, you know, a pragmatic randomized trial. We found many hundreds of them. When we looked more carefully, very few of them are really pragmatic. It's just that it's a nice thing to say. I'm doing a pragmatic randomized trial. And then you start reading, you see it's not pragmatic. Sometimes it's not even a randomized trial, actually. Patient-centeredness. Have we asked patients what do they care about? And you can think of the equivalent for other research fields. What does the community expect from us? We need to teach the community, but it needs to be bi-directional. We need to hear what people are interested in and how science can make their life better, longer, and more worthy living. Is it worth the money? There are formal ways to check for that, but very rarely is this done. Is it feasible? About 35% of surgical randomized trials are abandoned because of futility. And when you look at more exploratory designs, probably the abandonment rate would be much higher. And finally, transparency. We're back to that reproducibility, that trust component. Is there transparency? Is there some way that we can verify that the data, the methods, the analysis are unbiased enough that I can trust them? If you look across the board, very few studies fulfill more than 4 criteria. And if you know of any that fulfill 7 or 8, please come to me and let me know, because I'm trying to come up with a list of like the perfect studies. One might say, well, there's so much noise out there. There's about 35,000 official scientific journals. There's probably about 100,000 scientific journals if you add all the predatory ones and all the ones that would publish anything. Maybe I will just read very few. In case of medicine, I will read New England Journal of Medicine, Lancet, JAMA, PLOS Medicine, BMJ, Annals of Internal Medicine, maybe a couple from my specialty, and I will leave the rest. Well, if one decides to go down that path, 99% plus of the literature will be thrown away. Most of the good literature will be thrown away. I mean, these journals do publish a lot of good stuff, but there's lots of very nice papers scattered all over the literature. And even in these top journals, there was going to be very few studies that meet a lot of these criteria. Most would be desperately low scoring. This is some empirical data. How many of you are familiar with the Cochrane database? Okay, so most people. It's a very respectable database done by volunteers who have contributed effort and usually with very good methodological guidance and review to try to collect information across the literature, despite some bad news that we've had recently at the executive board level, but that's a different story. And we took a year and a half of systematic reviews on 1,400 topics, roughly. We asked, how often do you get to see high quality for the primary outcome? About 60% of the time, 57% of the time, there was no grade assessment. Grade is the grades of recommendation assessment, development and evaluation tool. It's a standardized tool that has been developed over more than 10 years now. It's very good to apply. And when it was not applied, the main reason was that there was no evidence to talk of. There was nothing to appraise. When it was applied, we found that only about 13% of the time, the quality of the evidence was high for the first listed primary outcome. It was a little better, about 19%, when you looked at any primary outcome, at least one of them having high quality, but still the minority. Now, if you asked for high quality of evidence, statistically significant results, and someone concluding at the end that this is an intervention that you should go ahead and use, there were only 25 such cases. 25 out of almost 1,400 is less than 2%. So less than 2% of the medical interventions had this solid, high-quality, action-prone, action-recommended evidence available. You may be familiar with hierarchies of evidence. Usually they're described as pyramids, and these pyramids change over time in terms of how the different levels are named. I think that meta-analysis and systematic review is still at the top. Randomized trials are next. Then you have observational studies. The bottom of the pyramid has been changing. I mean, it used to be experts. I think now we have tweets as well. And lots of sand around the desert. Evidence is clearly very often less than optimal, and we're missing lots of the upper echelons. And very often we see what I call MMM, not M&M. It's the medical misinformation mess. It's not just about science. It's about science plus healthcare plus patients plus people. There's 4 features to that. Most published research is not reliable or is of uncertain reliability, offers no benefit to patients, or is not useful to decision makers. Pretty much what I showed you already. Most healthcare professionals are not aware of this problem. I have failed completely. What can I say? Even if they are aware of this problem, most healthcare professionals lack the skills necessary to evaluate the reliability and the usefulness of the medical evidence. And finally, patients and families frequently lack relevant, accurate medical evidence and skill guidance at the time of decision making. So how do we overcome that? We need to have the right allies. We need to have stakeholders who are aligned with an effort to get truthful and also useful results. Now, depending on what field of science you're working, some allies are more powerful than others. For example, in medicine, the industry is very powerful. And the industry is probably under at least as much pressure to deliver results as academic researchers. And this is what they do. So this is an empirical evaluation where we looked at head-to-head comparisons in fairly large sample size randomized trials where you had a sponsored drug versus some other, and what was the nice looking outcome was that the sponsored drug is not worse than the standard comparator. Almost 97% of the time, the result was favorable. You know, the sponsor was right. I would argue if we have a study design that has 97% quote-unquote success rate, we can skip that step. We don't want it. You know, why should we waste money? We can just say the study is going to be successful. Let's put our money on something else. Do they cheat? No, I don't think so. I think that they just designed the study in a way that it is expected to have a 96, 97% success rate. You just have, for example, a non-inferiority margin that is large enough that almost any result will fall within that margin. Meta-analysis comes to the rescue. It's at the top of the pyramid. And I love meta-analysis. I have published a lot of meta-analysis. I don't know how many of them are true, let alone useful. But this is an assessment of the status of meta-analysis. There's about 100,000 meta-analysis published out there and about 250,000 systematic reviews. In an evaluation that I published in Milbank Quarterly 2.5 years ago, I found that there are many that are unpublished, actually. There's many that are redundant and unnecessary. For example, recently I wrote an editorial for a topic on oral anticoagulants for atrial fibrillation. There are practically 4 trials and 57 meta-analyses. And they all show the same thing, pretty much. Surprise, surprise. Many are decent but not useful. You say, wow, that was a lot of effort. Good for you, but so what? Lots of misleading abandoned genetics. Even though genetics made tremendous progress since the slides that I showed you, there's still lots of meta-analysis that put together little bits and pieces of genetics and genomics, and usually it's just publication bias that you see. Many that are flawed beyond repair, and about 3% that are both decent and clinically useful. So how do we sort that 3% and make use of that? One option is that we go a further step and we ask for guidelines. We try to put faith in assessments that do consider meta-analysis and then also take the extra step to tell us, so how much should you believe and how much should you act based on what you see? Unfortunately, 85% of guidelines are completely non-trustworthy. They have multiple red flags, including the sponsor is a professional society that receives substantial industry funding, the sponsor is a proprietary company or is undeclared or hidden, the committee chairs have financial conflicts, multiple panel members have financial conflicts. Any suggestion of committee stacking is obvious that people were asked to participate because they knew that they had a particular opinion about what to recommend ahead of time. No methodologists involved, no external review, and no inclusion of non-physician experts and patient representatives and community stakeholders. About 85% have one or more of these problems. And recently, I did some empirical evaluation of the most influential guidelines. Typically, these are cardiology guidelines, and I found that more than half of the most highly cited papers across all medicine are professional society guidelines in cardiology. 19 of the 20 most cited papers of the European Heart Journal in the last decade are guidelines, and one is a disease definition, which caused a 10-fold increase in the impact factor of that journal. And the societies that support this guideline activity, American Heart Association got more than $200 million from the industry last year. European Society of Cardiology, 77% of its budget comes from the industry. I would argue the rest of the budget actually also comes from the industry. For example, if you have a mega meeting of 40,000 attendees and they pay registration fees to go there and hear about industry products, it seems that the industry has not given these registration fees, but actually indirectly it has. Some other solutions. There's lots of solutions to these issues. And I think that is inherent in science to find solutions to problems. This is why we are trying to improve the work that we do continuously. Science is self-correcting. I think that we have an opportunity to learn from what other disciplines have done, what has worked, and try to see if it can be transplanted to other scientific fields. However, many solutions that are being proposed, including, I'm sure, several that I propose, have no evidence to support them. They need to be tested. So I would argue that we need to be very cautious about which ones we implement immediately and which ones we just ask for more evidence before we say that it's a good thing to do. This is a list of 12 families of solutions. And some of them have already appeared in the first part of the talk until now. Large-scale collaborative research, adoption of replication culture, registration at multiple levels, sharing of data, protocols, material, software, other tools, reproducibility practices, containment of conflicted sponsors and authors, more appropriate statistical methods, standardization of definitions and analysis, more stringent thresholds for claiming discoveries or successes, improvement of study design standards, improvements in peer review reporting and dissemination of research, and better training of the scientific workforce in methods and statistical literacy. Let's take a look at a few of them more closely. I'm very much in favor of large-scale collaboration. I recall that when I started creating consortia in epidemiology in the 1990s, people looked at me as, this is completely crazy, and what are you going to do? And, John has lost his mind. Now it's the norm. I mean, in many fields, you cannot do research unless you have large-scale collaboration. I think that this is a very good thing. When we do build these consortia, we go through an early phase where typically everything that we thought we knew collapses. For example, in genetics of smoking cessation, we thought that we had found 359 genes that regulate smoking behavior, and these had been published in top journals. We merged all our data, all of them went away. And 4 new appeared, and now we're adding more, and we'll get back to 359 pretty soon. Registration. Registration, I think, is a good idea, but it needs to be tailored to the particular needs of the field. Lots of research should not be registered because it cannot be registered. If I do exploratory research, the only thing that I should say is that this is exploration. There's no way to register exploration, and it may give a very misleading message if someone says, yeah, I mean, all of that was registered. It was not. Level 1 would be registration of a data set, which is a little bit like mapping a nuclear arsenal. So I can tell you that I have these databases in my computer. They're equivalent to 5 trillion of chi-square tests. So tonight, if I'm in a bad mood, I can press that button and launch these trillions of chi-square tests and their p-values against you. It's like mapping how much firepower is possible to generate from a data set. Level 2 is registration of a protocol, if a protocol exists. Level 3 is both the protocol and the analysis plan, because very often you see a protocol that is 100 pages long, but there's no analysis plan. And then level 4 is both the protocol and the analysis plan and the raw data, so that someone could spend time and look at whether you can get the same result reanalyzed. Level 5 would be open live streaming, like in the case of NASA publishing a paper in Science claiming that they had detected in Lake Mono some bacteria that were proof of alien life because they could use arsenic in their backbone instead of phosphorus for DNA. And a professor from UBC went through the steps of communicating with the entire world in public view every day. These are the experiments that I plan to do, getting feedback, amending them, running the experiments, getting more feedback until proving that actually these alien life bacteria did not exist. Analysis plans are something that is very dear to me. I love analysis. I mean, I'm probably addicted to numbers. When I was 8 years old, the best birthday gift that I got from my parents was the National Statistical Survey volume. Play with numbers. But I know that if you can play with numbers, you can get almost any result you wish. And this is what the situation looks like in observational research like epidemiology. If you want to address whether specific nutrients are associated with the risk of death, and you have a very nice database like the National Household Survey, which is extremely well surveyed and extremely well constructed, you can run 1 million analysis associating the levels of a vitamin, like vitamin E, alpha tocopherol, with the risk of dying. And how do you do that? You just adjust for any combination of 19 possible other covariates that affect the risk of death. And there's more than 19, actually, things that affect the risk of death. So if you add or not, each of these is 2 options. 2 to the 19 is about 1 million. And this is, if you look at the far right panels, you have the hazard ratio on the horizontal axis and the minus log 10 p-value on the vertical axis. 70% of the results suggest that vitamin E decreases the risk of death. 30% of the results suggest that it increases the risk of death. So you get what I call tremendous vibration of effects, and you get a Janus phenomenon. Janus was a Greek Roman god who could see in two opposite directions. Depending on what you like, you can pick the result that you wish and report that vitamin E increase the risk of death or decrease the risk of death or has no impact on the risk of death. And I think that this is how you get this type of science circulating. This is one of the top 20 altimetric impact scores across all science last year, claiming that with 3 cups of coffee per day, your risk of death decreases by 17%. The problem is that it decreased by 17% with whole grain, with beta-carotene, with alpha-tocopherol, with not eating 2 slices of bacon, with 1 ounce of meat less. Anything can give you that benefit of about 17%. And I think that the reason why relatively similar fields have different levels of credibility, if you compare, for example, air pollution epidemiology, where I believe that we have very high credibility that air pollution does kill people, versus nutritional epidemiology, you see that there are differences. I think it's an issue mostly of availability of raw data, availability of protocols, the ability to reanalyze the raw data, and the ability to run the reanalysis by contrarian teams showing consistent results. In air pollution epidemiology, this has happened. And even contrarians eventually got the same result. And they found that yes, air pollution does kill people. This has not happened in most of nutritional epidemiology because these databases have not been shared by contrarians who don't believe that coffee improves your life expectancy by 17%. There are other fields that are experimenting with sharing information. Clinical research has been going through some soul searching. We were all hoping that it will become the norm, that all data from clinical trials will become available, raw data. It has not happened yet, but we do see steps in that direction. Here's one step. This is study 329. It sounds like a submarine, a U329, but actually it's a study of antidepressants, paroxetine and imipramine versus control for adolescents with depression, major depression. It was published in 2001 by Smith, Klein, Beecham, and showed that both antidepressants are very effective and very safe. 15 years later, the raw data were reanalyzed, and the conclusion was that both antidepressants were not effective and not safe. Exactly the same database, exactly the same research question. How often do you see that discrepancy if you start making data available? A few years ago, we tried to see all situations that were pretty much like that, someone reanalyzing the original data a second time. And we found 37 such publications across medicine of randomized trials that had been reanalyzed for the very same question as the original. 35% of the time, we found that the authors of the reanalysis had a different conclusion compared to the original. So the original said the drug is effective, the reanalysis said it's not effective. The original said it's good for elderly people. The reanalysis said it's good for people less than 60 or 70 years old. Who were doing these reanalyses? Almost always it was the original authors. And why did they get these very confusing messages? I bet that we were just seeing the tip of an iceberg. Many other people were reanalyzing their data. And if they did, and if they found the very same result, it would be extremely unlikely that they would publish that again. They would get a response from a journal that we're not interested to publish the same result twice. Those that could come up with an ingenious analysis plan that could yield new insights, even though they're confusing, they could get that published. So can we have a more unselected view of how reanalysis could be performed? BMJ and PLOS Medicine allow us to do that a little bit, because in the last 4 years, they have asked for the raw data to be a prerequisite for publication for all the clinical trials that they publish. So we did go to all of these authors and we told them, can you please give us the raw data as you have promised, and we will reanalyze your randomized trials. Now, someone hearing from me that I want their raw data to reanalyze them may sound a little bit like being approached by IRS, but nevertheless, 46% of them did send these data, and we could reanalyze them, and we found no situation that the reanalysis reached a different conclusion. We found several situations of some errors which are human, but they did not affect the major conclusion of the study. Again, this is not necessarily a non-selected sample. It's a sample that you have 2 journals that have transparency policies. It's also the researchers who are willing to share, and hopefully they do check what they share with us before they send it out, and they feel confident that they can share it. But if you have that in place, you can reach a situation where you reach pretty much the same conclusion in these reanalyses. Who's going to do that? If you ask single teams to do everything for sharing their data, it's not going to happen. So it needs to be something that is embedded somehow in the collective decision-making of funders, all stakeholders who are interested in promoting research. So universities, research institutes, funders, journals, they all need to agree that this is a good thing. A few days ago, we published a paper in Science. We have about 40 authors in the masthead. We argue for making publicly funded data immediately available when it comes to genomics, but I would say also in other fields. Immediately means that the data generator has not a single day advantage over other people to analyze the data. Why is that? Because many types of situations arise, and it's becoming increasingly common, that the data generator attacking a slice of data is going to be a very inefficient approach compared to just making very large collections of data from hundreds of teams that can be cumulatively, communally analyzed with proper credit to all the data generators for what they have generated and for what they have done. But it's something that it needs to be agreed upon at a community level. It's not something that any dictator or any single team or any single university can impose, although single scientists and single institutions can really help to push in that direction. Here's another experiment that I did with Tom Hardwick, who recently moved to Berlin, where we're launching a new Metric Berlin Center, very similar to Metrics at Stanford. We took the highest impact, the highest citation papers from psychology and psychiatry, and we asked authors to share their data in public, and this is pretty much what we got. Some were already sharing their data. A few more were willing to offer that information, and we did get that, and we did make it publicly available. Still, many, though, would not share the information. And this is the creme de la creme. These are the papers that are the most influential in these disciplines. Why was that? Key reason, sharing was outside the researcher's control. We communicated with a corresponding author, with a guarantor, and we realized that the guarantor probably hasn't seen the data sometimes. It's not uncommon to have clinical research, and perhaps this is true also in other fields, where the guarantor is just a very busy person, very famous, but never saw the data. They got some analysis done by the company who was sponsoring the trial, and then the paper was published, but never really had a handle on the data. Legal or ethical concerns, of course. This is important. If the informed consent says that these data are never going to be shared, we cannot do that. Or, well, you need to reconsent. There's other options. We need to think of that ahead of time as we run new studies. Preparing own sharing system. This is what I was talking about, efficiency, who's going to do it. Data no longer exists. They were eaten by termites. That was a reason for a paper in The Lancet that the investigator said that the data don't exist because they have been eaten by termites. Insufficient resources and researchers still using data was pretty much the exception. Over biomedicine at large, we do see movement in these transparency and sharing practices. When we did an empirical evaluation of a random sample of papers published from 2000 to 2014, we found that practically nothing was being shared, and very rarely we could find a protocol. We found one study that shared a protocol, and that was a full protocol, and that was a separate paper. So the protocol had been published as a paper. Moving forward to 2015-17, we recently published the results of that survey that we had 18% of a random sample of papers published in these years that shared raw data. Still not much movement on the protocol side, but clearly there are incentives, there are efforts, there are many people who are arguing that more data needs to be shared. Psychology is a nice example. You can see here psychological science is the thick line, the proportion of papers that are sharing data once the journal adopted a policy that they want to share data. It starts going up within a year, and now it's at about 75% of the papers that they publish. This is our sample, where you see an increase from practically 0 in 2000. There were always few exceptions of some genomic data, but across the board of millions of papers, they would just get diluted, up to close to 25% by 2017. And also some other movement in some other transparency indicators. So we see more papers disclosing their funding. We see more papers disclosing their conflicts of interest. We still see most papers claiming that they have something novel to say, but we see a little bit of action on replication. Some papers that claim that they're replicating something interesting. Another group of efforts is focusing on reproducibility of computational methods. And there's many ways that can be improved to make sure that we don't have just the data, but we have the software and the script whenever there is software and script, and this is becoming more and more common. We wrote these recommendations a couple of years ago in Science, and we recognize that it needs to be a time process of moving through different levels. The simplest level would be if there's a link that says the software is here and the code is here, just click on it to make sure that it opens and you don't get an error sign. Whether we will reach the situation where someone will be always rerunning a script through some software and getting the same result, that might be a bit more questionable. But if you recall the paper that I showed you where there was a reproducibility effort of Science and Nature papers, 21 of them, actually everything was so transparently recorded that within a few hours, all these 21 studies could be rerun and verify that one gets the same result. So it was not really a lot of effort that was required. Better statistics and methods can also go a long way. We train people mostly to have expertise in subject matter and not on methods, and I think that this is a shame. We also train people in statistics light. We don't give enough emphasis on some design issues, on how to design studies, and I think that this is very obvious in what you see in the published literature. Are there easy ways out? No. This is an easy way out that I co-authored, realizing that it's an easy way out, and therefore not the perfect solution. Along with 71 other people, we argued that for now, if you're using p-values and you're using the magic threshold of 0.05, just move it 1 0 down. Make it 0.005. By doing this, you quote unquote kill about a third of the past literature. Overnight, just immediately 30% of the literature becomes suddenly non-significant or suggestive while it was significant. Some of that literature probably was true and potentially even useful, but if you look across the board, most of that probably was not. How often is using p-values and null hypothesis significance testing a good choice for any of these possibilities of doing research, like developing a prognostic score, assessing a diagnostic test, evaluating a therapy, mining electronic health records, or mining big data? Never. About 80% of the time, the best choice for statistical tools would not be null hypothesis significance testing. About 20%, it would be the best. So we need to train people to use the right tools, but you cannot do it overnight. We need a new generation. We need a new generation that's trained with stronger and not light statistics and with alignment of subject matter experts with data analysts. Until then, we have lots of options. I tried to review these options in JAMA about a year ago. None of them is perfect. All of them have their caveats, their strengths and disadvantages, but we clearly need to move somehow and make some progress. Containing the influence of conflicted stakeholders. I showed you examples where even if you have very well done research, if it is designed by people who want to get a particular type of result, they will get that particular type of result. So we need to agree as a community who is going to run particular types of studies. Who should be licensed to kill? Who should be licensed to design? To design randomized trials, meta-analysis, cost-effectiveness analysis, guidelines, or other sensitive studies. We have enough evidence that usually comes from reviews of trials when things become visible, or Freedom of Information Act situations where evidence becomes available about all the manipulations and the underlying pressure and the marketing pressure to try to get particular types of results, especially in medicine. Does this mean that we should be paralyzed? that we should wait for the perfect research before we can decide. Of course not. We need to make decisions right now. There's urgent decisions that need to be made. We have very strong evidence on lots of things. We have strong evidence that smoking is killing people, that climate change is happening, that. We need to act on that. We need to act even on things that we don't have certainty. But we need to recognize how much uncertainty is there with us and kind of modulate the message that we give to the community and also the actions that we take in trying to get that message through. We need more research on research. This may sound like give more funding to my center, but let's avoid that conversation. Practically, we need to study some of the research methods that we're using. We need to study some of the research methods that we're applying to study research itself. And there's lots of frontiers here. There's frontiers about how to perform research, about how to communicate research, about how to verify research, about how to evaluate research, and how to reward research. And I will close in the last few minutes with some comments on rewarding research. No matter what we do, if we reward bad science, we will get bad science. How can we tell? Well, no one is going to come out and say, I'm rewarding bad science. But we can model that. So we can build models that test different approaches to funding and rewarding investigation. And here's one such model that David Grimes and I built and we published about a year ago. It's 11 equations that we try to approximate the universe of science. And we start with 3 cohorts of scientists. We have a diligent cohort, a careless cohort, and an unethical cohort. Most people are very diligent. Some may be careless, so cutting corners at times, and very few, like 1%, are frauds. You know, science is not a profession that attracts fraudulent people. When it is revealed, of course, it hits the news, but I think it's one of the least likely professions for fraudulent people to flourish. We all have the same share of success if we deliver papers with nice-looking results. Now, when you run that model, it shows that over time, the diligent cohort becomes less populous, and the fraudulent cohort and the sloppy, careless cohort become more prominent. Why is that? You don't need 13 differential equations for this. It's just an issue that if I can get there faster by cutting corners or even by doing no work at all, just imagining that I have 500 participants, but they were never recruited, and I can get the same credit, you will get more of that. So how do we reward the best science, and should we also penalize bad science? I think is a very hot topic, and we don't have all the answers. I think we need to revisit what we are rewarding. Most of our systems are rewarding productivity, and I love productivity. I love writing papers. I'm an addict. Don't take that away from me. I mean, some people are saying you cannot publish more than X number of papers. I will commit suicide. But productivity is just one dimension, and productivity alone may actually be negative. I mean, if you just publish lots of noise and papers that make no sense. So we need to pay more attention to quality, to reproducibility, to sharing, and to translational impact. The full electrocardiogram is PQRST, and if you have the initials from these terms, I think we need to give value to these additional features. How do we do that? You can think of that as a currency exchange or a stock market. So the first column here is what is happening in most of our academic and research systems. Publication has value, so if you publish a paper, a good paper, you get 1 point. It doesn't matter whether it's replicated, translated, or refuted. If you share, if you contribute to community, like peer review, if you educate other people, if you're a good mentor, who cares about that? If you get a grant, an R1 is 5 points, like 5 good papers. And then you can buy wealth. You can become an assistant professor with 3 good papers. Well, depends on the university. Sometimes you need 50, but that's okay. 10 for associate professor, 20 for tenure. And if you have a doctoral student or a postdoc, you get 2 points. You can sell your slave and get 2 papers or vice versa. And if you get power, if you become president of the university or dean, you get 200 points because you have lots of money that you can disperse whichever way you want. Now, the second column is introducing some change. It says that publication has no value in itself, But if it is replicated, then it gets 2 points. If it is translated, then you get 5 points. If it is refuted, you actually start losing points. And all these other community-oriented efforts to improve science at large, get points. You can still buy your wealth items, and just having power doesn't give you points on its own. The last column is even more disruptive. It says that if you get funding, then you're losing points, because now you have all this money, and you need to do something with that. Why are you not doing something good for the community and for science? And obviously, if you have lots of money, you have lots of power, you lose lots of points. Is that viable? I think that we need to tailor our approaches and see how much of that can be applied realistically, how much of that is utopian. What are the steps to try to get more reproducible, more trustworthy research, and how do we need to adapt our reward systems? We have lots of problems, but we also have lots of opportunities to solve them. We can attack these problems at multiple stages in the cycle of generating ideas all the way to generating results and papers. And we need to get understanding and involvement of all the stakeholders. It's not just scientists. It's lots of other stakeholders. It's the industry, private investors, public funders, not-for-profit funders, journal editors, for-profit publishers, professional scientific societies, universities, not-for-profit research institutions supporting non-scientific staff, hospitals for medicine, other financial entities like insurance that are affected, government, state, federal authorities, people, consumers. They have very different visions about what science is. Why do we need science? Why do we need biomedical science or other types of science? What do we want to get out of it? Do we want to get papers? Do we want to get funding? Do we want to get deliverables, something that works? Do we want to save lives? Do we want to make profit? All of these are perfectly fine, but we need to find ways that they would be aligned and we would get the best possible. To conclude, the reproducibility and the usefulness of many scientific disciplines can clearly be improved. I think we're doing less than we could, and I'm not blaming anyone. I'm blaming myself that I'm working on that topic for so many years and I haven't made much progress. There are many possible interventions that may improve the efficiency of research practice and the reproducibility and the utility of the evidence. Transparency, openness, and sharing is likely to help, but details on how to can still be important, and I think that we need to figure those out. Empirical research on research is needed, and finally, decisions for policy, of course, should not be paralyzed because evidence is suboptimal, but we should acknowledge how suboptimal it is. I will close with special thanks to some of my colleagues who have collaborated with me in some of the empirical work that I shared with you today, and thank you for listening.
Going around, so if you ask a question, please use the microphone.
Hi. Thank you so much. That was just totally fascinating. You said something right near the beginning of your talk that I think you said, well, I always argue we need more money for science. And as a humble taxpayer, I'm trying to square that with pretty much everything else you just said. But seriously, it seems like we are investing poorly. And there may be some small bits of progress, but it's a system that really needs to improve itself a lot, especially given that the money is not a bottomless, renewable resource.
Yeah, of course. I think that maybe I'm biased in this statement because I'm a scientist, so I cannot say that we should not fund science. I definitely see your point about efficiency, and I think that this is exactly why we need to improve our efficiency. We need to improve our standards. We need to make a more convincing case that indeed that taxpayer money is being used in the best possible way. And I think there's lots of success stories that we can put forth for science. I mean, most of the things that are good for us have some scientific enterprise in terms of improving the quality and duration of our lives. At the same time, it would be a very convincing argument to make that we do see what are the challenges, what are the problems, and we're working on them. And we're very actively and eagerly working on them. I think that this is the best argument that we can make to taxpayers why it is better to invest in science, because it's fundamentally trying to improve itself, it's fundamentally self-correcting from its very definition, as compared to many other entities that would never question what they do. You know, we'll just give me more, I'm perfect, which is completely different to the science mentality.
Thank you. Yeah, this was great. Sort of to piggyback on that question, you know, to what extent do you think NSF and NIH have these issues on their radar? You know, sort of the top leaders of those, you know, the funding agencies. You know, do you think that you know, there are things they could do, you know, promote best practices or sort of, you know, change incentives, like some of the things you said at the end? Is this an issue that they're sort of aware of and thinking about?
I think that they're aware of it. I think that they're very sympathetic, and I think that they're taking steps in the right direction. NIH and less so NSF are very big ships and very difficult to turn. So it's not easy to have your full dream materialize overnight. You need to convince lots of stakeholders that this is the best way of action. There's some sense of not harming the enterprise. And of course, there's also lots of vested interest by even researchers who want to defend some of the status quo if it's working pretty well for them. For example, one of the most tenuous and difficult types of discussion is how do you change investment in fields that seem to be very inefficient in developing what they promised to do. I think that there's many such in biomedicine. It's not just an issue of, well, science will pay off in the long term. I think we're investing tens of billions of dollars on fields that we have tested them out and we know based on these results that they will not work. But if you have that knowledge and at the same time you have tens of thousands of investigators working on these fields and they know that if they change field, they will penalize for that. You know, they will be told by the study section, yeah, you're doing something different now. How come? You know, stay the course. This is a very incongruent schizophrenic message. So we need to help funding agencies add more flexibility on what they do and give them more freedom to apply some of these reforms that I believe that their leadership has endorsed and they do want to endorse, but it takes time to get them through the machinery.
Yeah, I wonder if you can address the issue.
You can address the issue of effect size. So it's often said that you don't need a randomized controlled clinical trial to prove that a parachute is useful, right? And when you see very large magnitude effects, you don't really even need statistics. It's fairly obvious that you've got something here that actually works. On the other hand, we're spending so much time discerning very small differences, and then when you calculate the number needed to treat, it's a shockingly high number, and I'm thinking, well, why even bother spend the money? Why should I subject my patients to the risk for this? So should we be focusing on things that are just really obvious and out there and not try to look at these minuscule differences that at the end of the day probably don't make any difference?
Yeah, I think that that's a very interesting question. You can study parachutes in terms of their effectiveness. Actually, there was a paper published in the BMJ last month in the Christmas issue. It was a randomized trial testing the effectiveness of parachutes jumping from an airplane. And the conclusion was that parachutes were not effective. There was no treatment effect. Neither the parachute group nor the control, no parachute group, had any problems jumping off the airplane. But the difference was that the airplanes were landed at that time. And there were some generalizability issues compared to airplanes that fly at 10,000 meters altitude. Are there big effects out there? Or have we found them all? I think this is the first question to ask. Are there lots of things like smoking causes cancer, which actually we cannot even do a randomized trial because it's a harm, or at least something that's very beneficial that has such a big treatment effect that we don't need randomized trials? Paul Glasziou has been compiling a list of large treatment effects. He has come up with about 20 interventions that have very big effects. Independently, along with Ben Dulbekovic, we have done some work to try to see how often we get some very large effects in licensed treatments. They do occur sometimes, but they're very rare in the overall scheme. And even in randomized trials, when we looked at 250,000 randomized trials, we saw that 10% of the time a large effect was seen, but when it was retested, it almost always went away. So it was just a winner's curse of a small study of 10, 12, 14 people finding something tremendously big, then it just shrunk or disappeared. So if almost all of the effects, or all of the effects, are small and modest, should we quit? I wouldn't say so, because small and modest effects could still be influential, either alone or in combination. So I wouldn't kind of say, oh, nature was bad with us. Everything we are surrounded from is tiny effects, so don't bother. If we can combine clusters or composites of tiny, small, modest effects, maybe we can still make a difference. And I think that this is probably what makes most sense. And much of that philosophy is aligned with more bird's eye views, both on risk factors and interventions rather than one at a time, which has been the paradigm creating the disasters of nutritional epidemiology, for example, and other fields.
Yeah, I'll just respond to that with one very quick comment, and that is that I treat patients with migraine headaches, and we have lots of drugs that have little effects. And I use them in combination oftentimes with no evidence whatsoever, because combination trials are never done. So that to me is another really critical area, is to figure out how we can add these small effects together and really have a positive benefit for patients.
We have time for one more question, and then there'll be a reception outside where there'll be more opportunities for people to talk to you.
Yeah, I may have gotten lost a bit, but are these only human studies, or do they apply to animal studies that you were talking about today?
So we have a lot of empirical evidence on animal studies. There's a lot of animal research that is being done, and there's lots of people who are empirically trying to assess how to improve the efficiency, trustworthiness, diminish bias in animal studies. And I think that we have seen substantial progress on that frontier. For example, most animal studies until recently were not randomized. They did not have blinding of investigators who were reading the outcomes. And these are easy steps to do, much easier than humans. We start seeing much more attention to these issues over time.
Well, practically anything is easier for animal studies as far as I can see. And of course, I've been working with air pollution, so there's always this issue of whether we want to rely on the human studies, actually epidemiology, or the animal studies.
Yeah, I think that animal studies are extremely important, and I know that they're under attack very often, but they offer some very nice base factors, talking methodologically, that can modify the odds of what you want to test next in humans. So I think that we just need to optimize the way that they're done so that we get the optimal base factors from their contact to inform us what to do next, and if we do need to do something on humans.
Okay, great, thanks. Thank you.
So I come from the social sciences, political science. We have reproducibility wars going on in the discipline, and those of us who are in the less quantitative side of the discipline find ourselves confronted with journals starting to think about, complete transparency of data when we've been doing this very qualitative interview-based work, and we have human subjects protocols and all the rest. Have you been tracking that, and have any thoughts about that side of the issue?
Yes, and in principle, I'm in favor of transparency. Does this mean that everything that is being proposed is going to work or is efficient, or do we need all of that? I think that time will tell, and I think that as we are implementing different changes at journal level or at professional society level or discipline level, we need to have some history of the field of what is being done, at least observational, whenever possible, I would say also interventional in terms of testing some of these modifications with experimental designs. I think that this is true for any field, including social sciences, and I think that there's a lot of very interesting debate happening in your discipline.
Thank you very much.
Thank you.